All right, we are going to start our HL material by looking at the Born-Haber cycle. So here are the understandings that we're going to get into, as well as the applications. And here is some guidance for some helpful hints to help you along. So the first thing that I want to start with are some definitions. So we're going to be bringing back some information from topic 3, which was all about periodicity, that is going to help us with the Born-Haber cycle. So the first thing to know is the first ionization energy, that is the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So we can see what the equation looks like for ionization energy. For example, turning sodium into a sodium ion. And then you see on the right-hand side the enthalpy of ionization. The second definition that you need to know is the first electron affinity. And this is the enthalpy change when 1 mole of gaseous electrons is added to 1 mole of gaseous atoms. So in the equation, we see that chlorine is gaining an electron to turn it to the chloride ion. And again, we see the enthalpy of electron affinity. Okay, one thing to note, ionization energy is positive. You have to add energy to remove the electron. For the first electron affinity, this enthalpy is always negative. Okay, energy is released when a nonmetal gains an electron to turn into an anion. Another definition that you are going to need to know is lattice enthalpy. So the lattice enthalpy is the enthalpy change that occurs when 1 mole of a solid ionic compound is separated into its gaseous ions under standard conditions. So for example, we could take any ionic compound and break it apart into its gaseous ions. Okay, so lattice enthalpy is a definition that you're going to need to know. So first, let's talk about how do we form and make an ionic compound. Well, from before, we know that ionization energy is always endothermic and the electron affinity is always exothermic. So if, for example, we take a look at those two equations from before and put them together, so let's say we combine sodium and chlorine, we know it is a highly exothermic reaction. In fact, it causes an explosion when it occurs. So you would think that the sum of the two enthalpies would be negative because it is exothermic. But if we indeed look at these numbers added together, you get positive 147 kilojoules per mole. So there's something going on. This isn't an endothermic reaction. Okay, the reaction, like we said above, is exothermic, so something else must be going on. So let's take a look at that. So the oppositely charged gaseous ions come together to form an ionic lattice. Okay, remember that is the repeating unit of an ionic compound. Okay, it has a highly uniform structure. Well, this is a very exothermic process as there is strong attraction between the oppositely charged ions. So, in fact, when we do take those two ions, the sodium ion and the chloride ion, combine them to get solid sodium chloride, we see that the enthalpy is negative 790 kilojoules per mole. Okay, that is how much energy is released, right, exothermic, when these two oppositely charged ions come together. So this is the key to why it is an exothermic reaction. We have the lattice enthalpy, or you might also hear lattice energy. that accounts for a big part of the total overall enthalpy. Now, there is a problem because lattice enthalpies or lattice energies cannot be directly determined, right? We can't go into the lab and experimentally determine it. An energy cycle that is based on Hess's law is used, and this is called the Born-Haber cycle. So in order to create an ionic compound, there are a couple steps that need to be done. So the first one is turning the elements into gases. Okay? We want gaseous ions eventually, while most elements are not gases in their normal state. So we turn them into gases. Then we take those atoms and turn them into ions in the gaseous state. This is where the ionization energy and electron affinity will play a role. And then finally, we can form the ionic crystal lattice. What we can then do is use Hess's law, or the theory of Hess's law, to figure out the lattice enthalpy, since we can experimentally determine all the other steps. So all of the steps that we can do, we have values for. Those are going to be in your data booklet. The lattice enthalpy is one that we can then figure out. So let's take a look at an example. Okay, so let's say we wanted to take that sodium and chlorine in their standard states and get solid sodium chloride. So there's going to be a series of steps, and then we're going to put them all together in a very large cycle. So the first step is to turn anything that is not a gas into a gas. This is seen in the first example here, where solid sodium is being converted to gaseous sodium. And this is called enthalpy of atomization. Okay, so that's given here by delta H with an atom. Okay, you see the symbol not, that just means it's standard conditions. Okay, usually this value is going to be given to you in the problem. Okay, chlorine in its standard state is diatomic and it is already a gas. Well, we only need one chlorine atom. So what we have to do is break that chlorine molecule into its chlorine atoms, and then we only need one of the atoms, so we're going to take half of that enthalpy. So the enthalpy is 1/2 the bond enthalpy. That's what that capital E means. That's bond enthalpy of the chlorine to chlorine bond. Okay, so we take 1/2 of the value for the chlorine to chlorine bond, which is 242. So now with these first two steps, we have one gaseous atom of sodium and one gaseous atom of chlorine. From the previous slide, we then turn those gaseous atoms into gaseous ions. So first we take the sodium and turn it into the sodium ion, and that is the enthalpy of ionization. That's positive 496. We want to ionize that chlorine atom, and we do that through the enthalpy of electron affinity. That's what that delta HE represents as electron affinity. Okay, these were two equations that we looked at on one of the previous slides. So up until this point, we now have our two ions, sodium and chloride, and then we can then bring them together to form our solid ionic compound, and this is going to be our lattice energy or lattice enthalpy. This is the unknown. This is what we are looking for. So those are some of the steps that we're going to be looking at, and there's one more that I'm going to show you on the next slide. So this is how we put it all together, okay? At first, it looks like a lot. But the good thing is all of the previous steps that we did are located on this cycle. We now just have to draw arrows to represent the enthalpy changes of each step. And as you can see, it forms a square or some sort of circular box. And that is going to be really important for our Hess's law. Okay, so a couple things I want to point out. We start with our solid sodium, and we only need one chlorine. So remember, it's 1/2 of a chlorine molecule. And what are we trying to do is we're trying to convert that into solid sodium chloride. So this is the one step that wasn't included on the previous slide. Delta HF is enthalpy of formation. Okay. Now this arrow is going down because it is an exothermic reaction. Negative 411 kilojoules, okay, are released. Okay, so that is why it is going down. So this is what we're starting with, and this is what we're ending with. Okay, but remember, this originally was a solid sodium and a gaseous chlorine, and we're making solid sodium chloride. We know that there are steps that need to be taken in order to get from here to here. And those are the steps that we just talked about on the previous slide. Okay, so we're going to take those steps and do them one by one. So the first step here is the enthalpy of atomization. That is where we turn solid sodium into gaseous sodium. Okay, each step of the cycle changes one thing at a time. The next step was breaking the chlorine molecule so that we could get one chlorine atom. That's where we did the 1/2 times the bond enthalpy. So here we're left with Na, that is a gas, and chlorine, that is a gas. So the next steps that we did on the previous slide was to turn them into ions. So here we have the enthalpy of ionization, right, or the ionization energy. That is also endothermic. We're adding energy, so the arrows are going up. For these first 3 steps, we are adding energy. So that's why the arrows are pointing up. So this step here has our gaseous sodium, but we still have a gaseous sodium ion, but we still have a gaseous chlorine atom. So we have to turn it into a chloride ion. Well, this electron that is shown, and that's very important that we show this electron from the ionization energy, this electron gets added to the chlorine, which turns it into a chloride ion. Now we can see that the arrow is now going down because this is an exothermic step. Electron affinity, the first electron affinity, is exothermic. So that's why this arrow is going down. So now we have our 2 gaseous ions, and our final step is to take the solid sodium chloride and break it up into its gaseous ions. So this is an important point. This arrow on the right hand side, the lattice enthalpy, where you see delta H LIT, is always going to go up because the definition of lattice enthalpy is to take a solid ionic compound and break it into its gaseous ions. So it's always going to be an endothermic reaction. So this answer should be positive. Okay. Each step, the value is either going to be given to you in the problem, or you're going to get the value from the data booklet. And now I can show you how we're actually going to take all of these numbers and calculate our unknown. How do we actually calculate the lattice enthalpy? Okay, so let's do this calculating the lattice energy or the lattice enthalpy. Well, the total enthalpy change of the cycle is 0. Okay? What this means is from our starting point, in the Born-Haber cycle, there were two routes we can take. What that means then is from the starting point to the ending point, the total sum is going to be 0, no matter which direction we take. What we are going to do is we're going to start with our elements in their standard state, and we're going to go in one direction, and we're going to, based on Hess's law, add any arrows going in the same direction, and then subtract any arrows going in the opposite direction until we get to our starting point. So, I'm going to go back to the previous slide. We're going to start with the elements in their standard state. And what I always do is start here and just go up. And we're going to add the enthalpy of atomization. We're going to add the bond enthalpy. The arrows are going in the same direction. We're going to add the ionization energy. Okay, same direction. We're going over here, we're following the arrows. Arrows going in the same direction, so we're going to add the enthalpy of electron affinity. Now here, you can see that we're going in the opposite direction of the arrow. So we're going to subtract whatever this lattice enthalpy value that we're looking for. And then I keep on going, following the arrow, and I'm hitting another arrow that is going in the opposite direction. So I'm going to subtract the enthalpy of formation. And now I've gotten back to my starting point. Okay, so again, you start with the elements in their standard state and you just go in a cycle, go in a circle. Follow the arrows and see, are they going in the same direction or going in the opposite direction? So if I do that, I get this equation. And all of that is equal to 0 because the total enthalpy change of the reaction is 0. We are looking for the lattice enthalpy, this delta H lattice. So this is what my x, my unknown, is. So I can rearrange the equation to solve for this. When I put everything to one side and get lattice enthalpy by itself, we get this equation. Then what I can do is just plug in the numbers from the cycle or from the data booklet or from the problem itself, plug in exactly what's given. And when we do this, we will calculate the lattice enthalpy to be positive 786 kilojoules per mole. Now, this is an equation that you should not memorize. If you focus on memorizing the equation, you will mess up some of the steps. I'm going to show you that in one of the problems that we have upcoming. Okay, it's easier to draw the cycle, follow the arrows, and remember, if they're going in the same direction, you add that value. If the arrow is going in the opposite direction, then you subtract it. So let's try and do one together. So there's certain parts that we're going to do, and then we're going to put them all together to create a Born-Haber cycle. Okay? You can either write the cycle down, or you can take a screenshot of the cycle, take a picture of it, and insert it into your notes. Okay? So each one of these parts gets into one section of the Born-Haber cycle, so we're going to use it in the full cycle that we draw. And then there is some additional data given to you. So the first thing that we're going to do is write an equation to represent the lattice energy of magnesium oxide. So, do you remember what lattice energy means? It is when you take the solid ionic compound and break it up into its gaseous ions. So when I do that, I would take solid magnesium oxide and break it into the magnesium ion, which is 2 plus, and then break it up into the oxide ion, which is 2 negative. Okay, so remember, this is the energy to go from the solid ionic compound to the separated ions in the gas phase. Letter B says write an equation to represent the second electron affinity of oxygen and comment on the relative values of the first and second values given in section 8 of the IB data booklet. Okay. Section 8 is going to be really important because it includes electron affinity as well as the ionization energy value. Now, oxygen, when it turns into an ion, is 2 negative. The first electron affinity is used to create a O with a -1 charge. That is the first electron affinity. The second electron affinity is to take that negative oxide ion, which is O negative, add another electron to turn it into O2 negative. The first electron affinity, like I said previously, is exothermic because we're taking a neutral atom and giving it a negative electron. The second electron affinity, if you were to look up the value in the data booklet, look at section 8 and find oxygen, you will notice that the second value is always endothermic because you're taking an ion that is negative and trying to give it another negative electron. So the first electron affinity is always negative, exothermic. The second electron affinity is always positive. If you have an ion like oxygen, you have to take both of those into account. Okay, letter C says use the following data and further information from sections 8 and 11 of the IB data booklet to construct a Bohr-Haber cycle for magnesium oxide. And then letter D says calculate the lattice energy of magnesium oxide. Okay, so some information that we're given because it's not found in the data booklet. We're given the enthalpy change of atomization for solid magnesium. Remember that is used to turn it into a gaseous magnesium atom. We are given the second ionization energy of magnesium. So the first value for ionization energy you're going to find in the data booklet. The second one is given to you here. And then we are given the enthalpy change of formation of solid magnesium oxide. So all of the information, you have to go to the data booklet or get the information from the problem itself. You can try to draw the Bohr-Haber cycle, use the previous example as a guide. But let's take a look at what we are going to do. Okay, you always start on the left-hand side with the elements in their standard state. From those elements in their standard state, we can then do enthalpy of formation to get the solid ionic compound. That is where the -602 comes into play. And we can see that the arrow is going down because it is negative. It is an exothermic reaction here. Okay, now let's start with our cycle. We are going to take solid magnesium, and if you remember the first step, hopefully, that is enthalpy of atomization. So we're taking solid magnesium here and turning it into gaseous magnesium, and that is positive 148. From the equation that we're trying to find, we only need one magnesium, which we have, and one oxygen. While oxygen is diatomic, just like the chlorine from before. So we only need one oxygen atom. Well, oxygen is diatomic, so we have to break that bond. So this step here is bond enthalpy. And we're going to do 1/2 of the bond enthalpy, or the bond energy it takes to break that bond, which is 498. That comes from section 11 in the data booklet. Okay, after these first two steps, we now have one gaseous atom of magnesium and one gaseous atom of oxygen. Once we have our atoms, we have to turn them into ions. Magnesium is going to turn into magnesium 2+. So that means we need to include the first ionization energy, 738, that came from section 8, and we're going to add it to positive 1451, which is the second ionization energy. And we're going to note that there are 2 electrons that were lost. So we do have to include that in our cycle. Okay, so this arrow going up is the sum of the first ionization energy added to the second ionization energy. So let's do our oxygen now. We have to turn it into O2 negative. The first electron affinity is negative. We get this from section 8 of the data booklet. The second electron affinity is positive. We also get that from section 8 of the data booklet. Now, if we were to add these two together, it is positive overall, which is why the arrow is going up. So this is one difference from before. Okay? From before, we only had one negative electron affinity, so the arrow was going down. This time, the arrow is going up. So now we have our 2 gaseous ions. Those gaseous ions come together to form your solid ionic compound. But remember, this is called lattice enthalpy, which is always defined as the solid ionic compound breaking up into its gaseous ions, which is why the arrow is going up. This is our unknown. As you can see, we have values for every other part of the cycle except this arrow here. So what we can then do is the math. So again, we're going to take our cycle, start at your starting point, okay, which is the elements in their standard state. And you're going to just follow the arrows, remembering to add the arrows if they're in the same direction, subtract the arrows if they're in opposite directions. Okay, so we add up the enthalpy of atomization, we add up the bond enthalpy of oxygen, we add up the ionization energy of magnesium, we add up the electron affinities of oxygen, we subtract the lattice enthalpy of magnesium oxide, and then we also subtract the enthalpy of formation of magnesium oxide and set that all equal to 0. So we plug in what we know, and we're going to solve for the lattice enthalpy. And when you plug in all of those numbers that were on the cycle from the previous slide, you get positive 3,800 kilojoules per mole. Okay, this is a very, very large number. Okay, something that we're going to come back to in another lesson. Okay, just one final thing to note before we look at some examples is we have to subtract the enthalpy of formation of magnesium oxide. Well, the enthalpy of formation of magnesium oxide is negative 602, so we're going to subtract a negative 602, so you end up adding 602 to the total. Okay, let's look at some practice questions. Number 42 says, identify the process which has the sign of its associated enthalpy change different from the rest. Okay, so one of these has an enthalpy change that is different from everything else. Okay, so look at all of the equations that are given. You should be able to recognize these and understand what they are, what they're telling you, and if they're exo or endothermic. Okay, well, letter A, you're adding an electron, which is electron affinity. Okay, it's the first electron affinity, which is always exothermic. So A is exothermic. That's negative. B, we're taking potassium and turning it into a potassium ion, and it's losing an electron. That is ionization energy. Ionization energy is an endothermic reaction. That is positive. Letter C, we have potassium chloride breaking up into its potassium ion and chloride ion. That is lattice enthalpy. That is a endothermic reaction. That is a positive value. Finally, letter D, we're taking a chlorine molecule and turning it into 2 chlorine atoms. So we took that molecule and broke its bond. Well, bond breaking is endothermic. That requires energy. It is positive. So B, C, and D are all positive, and A is negative. So that is the only one that is different. Number 43, which equation represents the electron affinity of potassium? Okay, well, although electron affinity is usually given for nonmetals, you can add an electron to any element. So which one is showing an electron being added? Well, C and D both show an electron being added. Only difference is C, we're starting with neutral potassium, and D, we're starting with a potassium ion. Well, electron affinity is when you add an electron to an atom. So that would mean C is your answer. Okay, number 44. Identify the process which corresponds to the standard enthalpy change of atomization of bromine. Okay, so atomization is when you turn something into a gaseous form, okay, from its standard state. Bromine, hopefully you remember, is a liquid in its standard state, so that automatically excludes A. But, well, it excludes A and C. Okay, so that only leaves us with B and D. But we only need one atom. So that means D is going to be your answer. We don't need 2 bromine atoms, we only need 1. From liquid bromine into standard state. Okay, 45 has 3 parts. Let's start with letter A. Write an equation to represent the lattice energy of potassium oxide. Okay, do you remember what lattice energy is? Right, when you break down that solid ionic compound into its ions. So you're going to take that potassium oxide and break it into 2 potassium ions and 1 oxide ion. Okay, make sure you note that there are 2 potassiums in potassium oxide, so you have to write that down when you write the equation. Letter B. The Born-Haber cycle shown may be used to calculate the lattice energy of potassium oxide. So what you have to do in B is identify the enthalpy changes labeled by the letters W, X, Y, and Z. Okay, so some values are already given to you, and we want to identify what each of these steps are. Okay, let's start with W. Well, in step W, we're taking oxygen, that oxygen molecule, and turning it into one oxygen atom. Okay, this is the bond enthalpy. It is also the enthalpy of atomization of oxygen. We just usually call it bond enthalpy. Okay, so that's where we take the oxygen molecule, we break its bond. Letter X. Okay, in this step, potassium is being turned into potassium ions. This is ionization energy. Now, in this particular case, we're going to multiply it by 2 because there are 2 atoms that need to be ionized. So we would look up the value and multiply it by 2 for each atom. Letter Y. After we've turned that potassium into ions, we have to do it for oxygen. So that would be the first and second electron affinities. Very last one that we need to know is Z, which is enthalpy of formation, delta HF. That is when we take the elements in their standard state and turn them into a ionic compound. So once we have done all of that, we now have all of the information that we need to do letter C, which is to use the energy cycle and further information from sections 8 and 11 of the IB data booklet to calculate an experimental value for the lattice energy of potassium oxide. So we can see from the cycle that the enthalpy of atomization for potassium is already given. That is 89.2. There's 2 potassium atoms involved, so we're going to multiply that value by 2. Okay. We need 1/2 the bond enthalpy of oxygen, so we have to look in the data booklet to get that. I already mentioned about the ionization energy, so you have to find potassium, find its value in section 8, multiply it by 2. For oxygen, you should be able to find the information from the data booklet in section 8, or we used oxygen in the previous example with magnesium oxide, so the information should be the same. And then the enthalpy of formation is already given as negative 361. Okay, so hopefully you remember the cycle. You start here with the atoms in their standard state, or the elements in their standard state. Follow the arrows going up. We hit this arrow, go in the opposite direction, so we subtract it. And then we hit this arrow for the delta HF, enthalpy of formation, and also subtract it, set it all equal to 0. If you do it correctly, you should get a value of 2,238 kilojoules per mole.